Okay, so once again, we're going to use the Mitchell-Benebow language to prove something that we know kind of should make sense in ordinary logic. But I mean, I think if you ask most people to sort of try and prove what I'm about to say using ordinary logic, they would, go to the law of the excluded middle, which we're not allowed to use. So, but it's interesting that we can get at this result nonetheless, because it's very kind of important and elementary. Um, and so basically, we want to prove this theorem here that if we have formulas phi and psi, we have that if not phi and phi or psi, then psi. Okay. So if I tell you I have a number and I say it's either an even number. So say if I have a number and I say that it's either an even number or it's 7, and I tell you that it's not an even number, then you know it must be 7. Okay, that kind of idea. So let's prove this. Now we're going to do it in steps and establish some useful results as we go. So firstly, we've got this kind of simplified cut rule, which we're going to make quite a lot of use of, which we've already seen, which basically says that when every free variable in psi is either free in gamma or free in phi, then we have that if gamma implies psi and psi implies phi, then gamma implies phi. It's very useful. And the first thing we're going to establish is this theorem 1 here. Actually, before we do that, let me just say something that we're assuming. We're going to assume the distributive laws. So that is for formulas A, B, and C, we have that A and B or C if and only if A and B or A and C, and also this other kind of law, A or B and C if and only if A or B and A or C. Now, it is possible to prove these laws using the basic kind of machinery of the Mitchell-Benebow language. The way I like to think of it is simply, well, kind of simply, that this category of that. I mean, these logical arrows. Like when we're comparing truth, we're really sort of talking about extensions of formulas over the same list of variables. So we're talking about sub-objects of a particular object. So in a way, we're kind of wandering around in this category, which has, let's say, sub-objects of X as its objects, and arrows representing containment of one sub-object in another. And I've already argued previously that that kind of category is Cartesian closed. And then the fact that the distributive law holds is evident from that. So, if we thought of these as sub-objects instead of formulas, and we replace the ands with intersections and the ors with unions, this would simply, well, then they would correspond to products and co-products respectively, and then this would just be the distributive law, which always holds for such a Cartesian closed category. So that's an easy way to justify this. Anyway, okay, got this simplified cut rule. Let's go on to our first theorem, which says that not phi or psi always implies that phi right arrow psi. So how do we prove it? Well, starting from no assumptions, we can get that phi implies phi trivially. Then using the using the not rule, we can get that not phi and phi implies false, which makes sense. Also, trivially, we get, using the kind of false rule, we get false implies psi. Also, starting from nothing, and then using the so then we can use the simplified cut rule, since false doesn't have any free variables anyway. So we get that this implies false and this implies psi. So we get that not phi and phi implies psi. Okay, which is kind of interesting. And also, starting from nothing, we get that phi and psi implies phi and psi. Then we can use the and rule here to change this into phi and psi implies phi and phi and psi implies psi. So we've got, just taking that bit, we've just got phi and psi implies psi there. And then we can just use the or rule. So we get that not phi and phi or phi and psi implies psi. Now, since we're saying we're assuming the distributive laws, we have this. So we've got that phi and not phi or psi implies phi and not phi, or phi and psi. So as I've argued up here from no assumptions, we've got that not phi and phi, or phi and psi implies psi. And since this orange formula up here always implies this formula in here, which in turn implies psi, we can use a simplified cut rule, because, you know, every free variable in here is free in here. So we get that phi and not phi or psi implies psi. And then we can just use the implied rule to get that not phi and psi infers phi implies psi, which is what we wanted. Okay, next thing we're going to use, so we're really sort of gathering together tools that we're going to use for our proof later on. And this is a nice thing about the Mitchell-Benebell language. You sort of, as you prove things, you usually want to work out more elementary kind of facts, and then you can use them again later. So you're kind of like building up experience. So here's another one. If A implies B and C implies A or D, then C implies B or D. So we suppose that A implies B, and we trivially get that B or D implies B or D. And we use the OR rule, so this becomes B implies B or D, and D implies B or D, and we've also got A implies B. and then since A implies B and B implies this, again, we can use a simplified cut rule to get that A implies B or D. And we also have from here that D implies B or D. And so we end up with A or D implies B or D. So now if we start with these assumptions that A implies B and C implies A or D, then we get A or D implies B or D, and C implies A or D. So we get that C implies A or D. I'm a little bit concerned that the simplified cut rule might not work here, but there's got to be a way around it. So, I mean, what we want to be able to do this kind of reasoning is that we want every free variable in A or D to occur in B or D or C. Well, it's clearly fine for D, but we want every free variable. So we need this extra condition that every free variable in A occurs in C, B, or D. Okay, so let me just quickly check. So we want this as an extra sort of because here's where I actually use it in my argument. So in my case here, I'm having A as false. Okay, I think. Yeah, I'm using A as false, so that's fine because it doesn't even have any free variables. So I'm okay in that usage. So let me just go back. Why do I say this? Well, in order to use the cut rule here, we're basically, simplified cut rule, we're basically saying, well, C implies A or D, and A or D implies B or D. So then we want every free variable in B or D to either be free in, sorry, then we want every variable free in A or D to either be free in B or D or to be free in C. Well, clearly every variable in D is going to be free in B or D, so that's fine, but we need every variable in A to be free in B or D or C. Okay, so it has to be free in one of these three formulas to use this. Okay, right then, theorem 3. Phi and not phi or theta implies theta. Okay, so trivially, we have false or theta implies false or theta. Using the OR rule, we have that false implies false or theta, and theta implies false or theta. Now, we can get from nothing, we can get that phi and not phi implies false. So we've got that false implies, and then we've got that false implies this stuff. So again, using simplified cut rule, we get that phi and not phi implies false or theta. And we've also still got theta implies false or theta. Now, using the OR rule, we have that phi and not phi or theta implies false or theta. Now, there's a step of reasoning star, which I'm about to explain, which then gives us that phi and not phi or theta implies theta from this. Okay. So let me explain this reasoning. Firstly, let me do this one in orange. So we have false implies false. So thinning, we have that true and false implies false. And so we have that false implies not true. Okay. Now, yeah, so we've got false implies not true. We've also got this from up here. That's what we want to reason from. So phi and not phi or psi implies false or theta. So we'll have this as C. We'll have A as false. And we'll have D as theta. So we've got C implies A or D. And also A implies B. So we get C implies B or D. All right, let me just make this more clear. A is false. B is not true. This is C. Here's A again. And D is theta. Okay, so then we get C implies B or D. Okay, and as I say, this works in this case because we do indeed have that every variable free in A occurs in C, B, or D because there aren't any free variables in false anyway. So yeah, we can then use this rule to get phi and not phi or psi implies not true, and theta. Now, a bit more reasoning. Starting from nothing. Well, we already proved this formula earlier that not phi and psi implies or always infers that phi implies psi. So using this formula, just this works for general formulas. So let's use phi equals true and psi equals theta. So we get not true or theta infers t implies theta. Then we can use the implies rule to get true and not true or theta implies theta. Well, doing a true with and just doesn't do anything extra. And you can see that, if you like, by thinking in terms of extensions intersecting with a maximal subobject doesn't change the subobject. And so this just becomes not true or theta implies theta. So again, we can do our simplified cut trick because this C here implies not true or theta, and that in turn implies theta. So we finally have theta, and so we finally have phi, and not phi or theta implies theta, okay? Which is what we wanted. So that gives us our final step in our reasoning and proves our claim that phi and not phi or theta implies theta. So okay, now we're ready to actually prove what we were after, which is that phi or psi and not phi implies psi. So let me just copy this so I can paste it down at the appropriate place. So okay, here we go. Starting from no assumptions, we get phi or psi and not phi implies phi or psi and not phi. Now using the distributive law, we have that this in turn implies phi and not phi, or psi and not phi. Now we recall theorem 3 here, and we'll use theorem 3 with this formula theta as psi or not phi. So you see it matches this pattern, so that's going to imply theta, which for us is psi or not phi. And again, it makes sense because every free variable in here is, of course, free over here. So we have phi or psi and not phi implies phi and not psi. And now finally, sorry, we have phi or psi and not phi implies psi and not phi. So finally we just use our AND rule here, and we've got that phi and psi and not phi implies psi, okay? And that's what we wanted. And we've got some other stuff as well. But this is what we're after, so that completes the proof.